Hi, hi. Okay, so last time we went over a nice geometry situation where we were trying to find the orthogonal projection of vectors onto lines, and then we went on to apply that to get the to take a regular basis and turn it into a basis that's especially easy to compute with, namely a basis where the members are all orthogonal to each other, basis for Rn, where all the members are orthogonal to each other, and in fact you can then go on to make them all have length 1 and get an orthonormal basis. So that's naturally the check-in asks for an example of that, so let's get to it. Okay, so let's see here if I can get the basis down. Let's see, the basis that I'm given is a 1 minus 1, 0, 2, 0, 1, 3 minus 1, minus 1. Okay. And those basis vectors are not orthogonal. Just as an example, if you take the dot product of the first two, you just don't get 0, you just don't. So we want to derive from this basis another one where the members of the basis are orthogonal, mutually orthogonal, pairwise orthogonal. So what you do then is the first basis vector of the new basis, kappa 1, will just simply be the first basis vector of the old basis. That is, you got to start somewhere. So our initialization is to start with kappa 1 equals beta 1. And then kappa 2 is you take beta 2, but that won't do because beta 2, that won't do by itself because beta 2 has some component in the direction of kappa 1. So this won't do for kappa 2. Instead, we subtract away the part of beta 2 that is in the direction of kappa 1. So let's see. That's 2, 0, 1 dot producted with 1 minus 1, 1. Oh, 1 minus 1, 0. I'm sorry. That's the top of the fraction. The bottom of the fraction is the dot product of 1 minus 1, 0 with itself. And this is multiplied by the vector 1 minus 1, 0. So I'm subtracting away the projection of beta 2 onto the line generated by kappa 1. So this is a multiple of kappa 1. I'm subtracting that away, and when I'm all done, I will have what's left in beta 2 when you subtract away any part in the direction of kappa 1. And I already did this out. So what did I get? I got 1, 1, 1. This is 2, 0, 1. Take away 2 halves of 1 minus 1, 0, and I got 1, 1, 1. Because if I tried to do this live, we'd be here for some time. So I worked it out in advance, and it comes out to be 1, 1, 1. So then kappa 3, a person can say, okay, but now you're starting to look at multiple interactions. Do I have to look at the interaction of the interactions? So that's why we go as high as 3 to do the general case. So kappa 3 is you start with beta 3, 3 minus 1 minus 1. And you subtract away the part of beta 3 that lies in the direction of kappa 1. So that's going to be, let's see, 3 minus 1 minus 1. Dot producted with 1 minus 1, 0. And on the bottom goes 1 minus 1, 0. Dot producted with itself, 1 minus 1, 0. And all multiplied by the vector 1 minus 1, 0. So this is the scalar and this is the vector. So this is the part of beta 3 that is in the direction of kappa 1. And now I'll subtract away the part of beta 3 that's in the direction of kappa 2. So 3 minus 1 minus 1. Dot producted with kappa 2, which is 1, 1, 1, 1, 1, 1. And then 1, 1, 1 dot producted with itself, 1, 1, 1, all multiplied by 1, 1, 1. I won't put a dot there just because I don't want to make the picture more confused than it actually is. And so I get here, this is 3 minus 1 minus 1. Subtract 4 halves. I know that's 2, but anyway, 1 minus 1, 0, and subtract away 1/3 times a 1, 1, 1. And when you do it all, you end up with what? 2/3, 4/3, no, 2/3, 2/3, and minus 4/3. Sorry about that. 2/3, 2/3, and minus 4/3. So the orthogonal basis is 1 minus 1 0, comma, 1 1 1, comma, and then 2/3, 2/3, minus 4/3. And a person can see that these are mutually orthogonal. Just to pick two, how about if I pick the second and the third? If you take the dot product of the second and the third, you get a 2/3, a 2/3, and a minus 4/3, and it comes out to be 0. So that's right. Now, I cautioned you a couple times that in the literature, if you go online, for example, you Google around, you may very well find that when authors use the phrase orthogonal basis, they often mean orthonormal basis. That is, they go on to normalize every one of these vectors. They find the length 1 version of all of these vectors. So I'll go on and make the orthonormal basis. And so let's see. So the length of that is square root of 2. So I'll multiply 1 over square root of 2 to get 1 minus 1, 0. That's the first member of the orthonormal basis. The second is got length 3. So length square root of 3. So 1 over square root of 3 is the orthonormal version of this. Is the normal version of this. And the last one is what 4 and 4 and 16 makes 24. So 1 over the square root of 24 over 9 by 2/3, 2/3, minus 4/3. And you can really see why authors consider this to be kind of a trivial step. There's no interesting content there. But in any event, this basis is especially convenient for many calculations because all of the members are orthogonal to each other and because all of the members have length 1. Okay, very good. All right, so we're moving on to a new chapter. So I want to talk about what's in the new chapter, and it's let's see, what's the right thing to say here? It's a straightforward idea, but it's one that the execution will be sort of doing something that you may very well not have seen before. That many folks in the room, almost everyone in the room, has not seen the kind of approach we're going to take, and so that can throw a person for a loop. So while we're going through it, I'll talk about the approach. That's of course not really mathematical content, but nonetheless, it helps sometimes to hear somebody say, at this point, you should feel, sort of stuff. Okay, so I'm going to start by pointing out the importance of the idea of non-singularity. We saw it right away at the beginning of the book. Non-singular is where you have a square matrix, a square matrix of coefficients it was at the beginning of the book, and you do Gauss's method and you don't have any 0 rows. So non-singular means don't have any 0 rows. Non-singular means sort of the kind of sensible, natural case. Of course, if you have 0 rows, that doesn't make it not unsensible, that doesn't make it ridiculous, but it just means that you expect to find unique solution, and non-singular is the case where you did find unique solution. Maybe it's a psychological effect, not a mathematical effect, but there you go. So non-singular, nice in some sense. Non-singular is equivalent to all of these things. Non-singular for a square matrix is that if you have a linear system, it has a solution and the solution is unique. Non-singular is equivalent to Gauss-Jordan reduction yields an identity matrix. So a person should be feeling, as we go through these bullet points, that every one of these is the nice case. The rows form a linearly independent set. The columns form a linearly independent set, which is a basis for Rn. Any map that is represented by T is an isomorphism. There's an inverse. The inverse exists. All of these cases give a sense of non-singular as whatever this means, desirable. Now again, in mathematics, we tend to avoid value judgments. But if a person is sitting there saying to themselves, I got this problem, and it would be great if the matrix turned out to have a unique solution, what you're thinking to yourself is it's desirable to have non-singular. Okay, so it's natural to be, you're looking at a matrix, let's say it's 20 by 20, and you're saying to yourself, I wonder if that fella is non-singular. So You can start in on Gauss-Jordan reduction or just plain Gauss reduction and look to see if you get any zero rows. That's a very sensible thing to do. But another sensible thing to do is to say to yourself, well, look, whether or not it's non-singular is a function of the entries of the matrix. So there must be, you think to yourself, there must be some formula that determines whether the matrix is non-singular. What's that formula? I'll just plug my entries into the formula. That's good. That formula is called a determinant because it determines whether the matrix is non-singular. So if a person was thinking to themselves, I wonder what the formula is, well, what would you do? You'd take out a pencil and you'd say to yourself, well, let's look at this. Let's look at the 2x2 and the 3x3, and we'll write down what the formulas are. We'll see the pattern. That's a good plan. We already saw the 2x2 case. A, B, C, D is non-singular. Do you remember that we did the inverse of the 2x2 matrix? And the inverse of a 2x2 matrix turned out to have a fraction in front of it. That is, it was scaled by a real number. The fraction was 1 over AD minus BC. So obviously, in that case, you run into trouble getting the inverse if AD minus BC is 0. That is to say, if AD minus BC, if you multiply A times D and subtract B times C, if AD minus BC is 0, you find there is no inverse. If AD minus BC is 0, you find that the matrix is not non-singular. Said without the double negative, you find that the matrix is singular. So AD minus BC unequal to 0 is the non-singular case, is the case we're looking for. Okay, so that's a 2x2. We already did that. So now you take out a 3x3 and you write down the letters A, B, C, D, E, F, G, H, I, and you start in on Gauss's method. You take, let's see, I want to use the A to get rid of the D. So you take a negative D over A times row 1, add to row 2, but somewhere on the piece of paper you write down providing A is not equal to 0, and you cover that case separately, sort of stuff. And you start in and you do Gauss's method to end up with echelon form, covering all the cases like the A equals 0 case. You do Gauss's method to end up with echelon form, and you get this for a formula. Just like up here we got this for a formula, it's the bottom of the fraction. Here we get this for the formula, that's the bottom of the fraction. Same thing for 3x3s, except it's more complicated and I'm not going to show you. So it's somewhat reminiscent of what's up there. There's a not equal to 0, so that's very suggestive. But it's a little tough, not a little tough, it's kind of a lot tough to understand what's happening on the left-hand side. Well, let's ignore that for the moment, and let's just say the not equal to 0 is a pattern, and then you fall back on the one by one case, and then the one by one case is very straightforward, but it also has a not equal to 0. So in our mind, in what I like to think of as my mind, I'll imagine a family of formulas. A, AD minus BC. This formula here, too, that I won't repeat. There's a different one for each size matrix. And each formula defines a determinant function, det sub n by n, that inputs n by n determinants and outputs a real number. And then we say to ourselves, in what way does it determine non-singularity? Well, the matrix is non-singular if and only if the determinant is not 0. So we're thinking that the pattern shown here, the 1, 2, 3 pattern, it would continue for all n. And in fact, it will continue for all n, but it isn't perfectly clear what the pattern is it? Okay, so the plan is that the formulas don't make clear what should happen in the general n by n case. So we're going to do something that you may very well never have seen before. It becomes sort of more standard in mathematics as you proceed up through more and more sort of advanced levels, but this is, for many folks in the room, this is the first time they've ever seen it. So I'm going to talk about it for just a little bit. Instead of writing down the determinant function is calculated by this formula, instead what we're going to do is we're going to say the determinant function is described by these conditions. And then we'll go looking for a function that satisfies those conditions. Eventually we'll come up with a formula, but we're going to start off by saying the determinant function satisfies these conditions. Okay, and those conditions will let us compute the determinant of a square matrix via the same way we always proceed, which is Gauss's method, that we know is fast and easy. Now, I want to spend a minute talking about writing down conditions for a function. So suppose I told you that I was looking for a function that takes in natural numbers 0, 1, 2, 3, and it outputs, when the numbers are multiple of 5, it outputs 0. You'd say to me, okay, you could do that. You'd say but there are lots of functions that do that. For example, there's the function that anytime you have a multiple of 5 outputs a 0, but anytime you have something that isn't a multiple of 5 outputs a 1. That's a perfectly good function, and it satisfies your condition. Another function that satisfies your condition is it always outputs 0 under any circumstances. So you'd say, well, that's true. Those are two different functions that satisfy the condition that I stated. That's true. So you might state some other condition. Okay. So I'm looking for a function now that if you give it a multiple of 5, it outputs 0. And if you give it a multiple of 2, it outputs 1. Okay, now you're in a different circumstance entirely, because instead of there being lots of functions that satisfy in this case, two conditions that you stated, now there are no functions that satisfy the two conditions, because what if you give the function 10? It's a multiple of 5, so the function should, to follow the first rule, output 0, but it's a multiple of 2, so it should, to satisfy the second rule, output a 1. So now there are no functions that satisfy the two conditions. So if you're going to say to me, I'm looking for a function that satisfies a list of conditions, okay, fair enough, that's fine, but you're going to have to go on at some point to verify that there is at least one such function, and also that there is at most one such function, because otherwise there could be many such functions or there could be none. So that's a situation you've probably never been in before. Probably in prior classes, Calculus 1 sort of stuff, whatever, you might have had like a combinatorics class or a statistics class. You probably, you write down formulas and then you say this formula describes a function. That's fair, that's great, but we're in a circumstance here where the formula is not clear. So instead, to describe the function, we're going to give a set of conditions, and then we'll use those conditions to allow us to apply Gauss's method to do the thing that you think we'd do. But because we are describing the function with conditions, we will at some point have to show that the function is unique. We'll do that today in this video. And we'll also have to show that the function exists. Okay, so that's the plan. Right? So we're going to have to show that the function is unique and that the function exists, and that's called showing that the function is well defined. Okay, so here are the conditions. I'm giving 4 conditions, and I'm saying that a determinant function has to satisfy these 4 conditions. And a person notices, you haven't had a chance to read it yet, but once you've had a chance to read it, a person notices that conditions 1, 2, and 3 are simply stating that in some way, this allows me to apply Gauss's method. What do you mean it allows me to apply? Well, condition 1 is really the first one. It's really the main one that we ever think about. If you do k rho I plus rho j to the matrix, if you do k rho I plus rho j, then you get the exact same result. The determinant of the matrix before you do k rho I plus rho j, here it is the same as the determinant of the matrix after you do k rho I plus rho j. And of course, k rho I plus rho j is that combination operation is the heart of Gauss's method. So if the determinant before you do k rho I plus rho j is the same as the determinant after you do k rho I plus rho j. And then, of course, the next 2 lines are going to say something about swapping rows and multiplying a row by a scalar. So I'll cover them in just a second, but the point is that these 3 are the steps that you need to do Gauss's method. So saying I want a function that satisfies these conditions turns out to be saying that I want to be able to perform Gauss's method on these matrices and use that to determine the non-singularity of the matrix. Okay, condition 2 is that if you swap 2 rows, see how it says rho I and rho j over here, and then over here it says rho j and rho I? So if you swap 2 rows, then you change the sign, the SIGN, of the matrix. So if the matrix had the sign of the determinant of the matrix, excuse me, I misspoke. So if the matrix had determinant 5, and then you swap 2 rows, the new matrix, the after you swapped it matrix, will have determinant -5. In the book, we go on, we do some examples to show that, in fact, that's what actually happens. So that's why this condition has the funny minus sign. You might say to yourself, why don't you just have an equal? And it turns out the equal doesn't give you what you want. But so certainly, if we're worried about being 0 or not being 0, changing the sign, changing the SIGN, doesn't affect being 0 or being not 0. And then condition 3 is somewhat reminiscent of condition 2. In the book, we go through some examples that show in the 2x2 and 3x3 cases, this is what happens. And so we project that this is what's going to happen in the 4x4 and the 5x5 and the 6x6, etc. In any event, what it says is that if you take a matrix and find the formula for it, the determinant, the function in this case, we're defining a function. If you take a matrix and find the determinant of that matrix, if you multiply a row by k, one row by k, not the whole matrix, one row by k, then you multiply the determinant, the entire determinant by k. So if, for example, you had a 4 by 4 matrix and you multiplied row 2 by 16, then you would multiply the determinant of the entire matrix by 16. So again, a person might scratch their head and say, well, why you don't need that? You could just say determinant after you multiply by k is the same as the determinant before you multiply by k. But the book goes through the examples that show, no, you do need this to cover the 2x2 and the 3x3 cases that we talked about. And besides, it's clear that if you're worried about non-zeroness versus zeroness, this won't have an effect. Multiplying by 16 won't change whether or not the matrix is 0. The determinant of the matrix is 0. Keep stumbling, I apologize. Whether or not the determinant of the matrix is 0, multiplying by 16 won't affect that. And then lastly, condition 4. I need the determinant of the identity matrix. So I'm going to do the simplest possible thing. I'm just going to provide the scaling factor of 1, that the identity matrix has the determinant of 1. If I wrote down here the determinant of the identity matrix is 5, then all the calculations we do in the rest of the chapter, and in fact in the rest of the book, would be bigger by a factor of 5. We're just going to take it to be 1. We often write here these up and down braces for the determinant of t. These up and down braces here might remind a person of absolute value, might remind a person of the length of a vector. So we have a general idea in mathematics of using these up and down braces to indicate size somehow of the included object. So the size of a vector is its length, the size of a number is its distance from the origin, and the size of a matrix, for reasons that we'll see in the next section, the size of a matrix is the determinant function. Okay. Okay, just a remark that condition 2, the condition about swapping rows, is redundant because you can accomplish swapping rows by using condition 1 and condition 3. So that's another thing about this minus sign in this k, is that in order to maintain consistency, you have to do certain things. But before we get into the details of that and get into those in the book, we really want to go on and calculate some things with the definition and get comfortable with the definition. So I'm going to take that, again, we're doing something that I don't know that a person has done before. So I'm going to take that definition, I'm going to provide a couple of results, and those results will enable me to calculate the value of the function. So again, I've defined a function, det, satisfying some conditions. I'm going to show in the lemma that we're about to look at, I'm going to show that if you satisfy some conditions, then it has these consequences. And we will use that to calculate the value of any function that satisfies those conditions. So something that a person has never seen before, recognize that, trying to help a person orient themselves. What the heck are we doing? What we're doing is, it's not clear what the formula is, so we're writing down some conditions. The conditions will allow us to do Gauss's method. That's how we ever determine non-singularity. All right, so just to go through them quickly here, I know a person can read, but a matrix with 2 identical rows has a determinant of 0. Just thinking in terms of non-singularity, that's what we want. If a matrix has 2 rows the same, then of course when you do Gauss's method, one of them would turn into the 0 row and you'd be singular. A matrix with a 0 row has a determinant of 0. Again, if you had a matrix that started out with a 0 row, you'd say to yourself, well, I know right away that's singular. A matrix is non-singular if and only if its determinant is non-zero. So that's what we want, that one there, that's the goal. And then finally, the determinant of an echelon form matrix is the product down its diagonal. So picture in your mind an echelon form matrix. Maybe you have sort of a 1, and then a 3, and then a 5 for a 3 by 3 matrix. 1, 3, 5 as the leading entries. The determinant of that matrix is going to be its echelon form, so it's got zeros below. Determinant of that matrix is going to be 1 times 3 times 5. Okay, so I'm going to verify the four statements one at a time. So to verify the first sentence, if it's got two identical rows, then it has a determinant of 0. So you swap the two rows. If you swap the identical rows, you get the same matrix. But one of the conditions says that the sign, the SIGN of the determinant changes. So the only way that could be is if the determinant is 0. For the second sentence, you have a row of all zeros, multiply by 2. One of the conditions says that when you multiply by 2, you multiply the determinant. When you multiply one row by 2, you rescale one row by 2. You multiply the determinant of the entire matrix by 2. But when you multiply the 0 row by 2, you get back the same matrix. So the only way that could be is if the determinant as a whole is 2. It's going to be 0. Sorry. Now, the third sentence, remember before I switch over, the third sentence says a matrix is non-singular if and only if its determinant is non-zero. So that's the one we're super keen on. So the idea is if you give me a matrix and I do Gauss's method on it, I'll start with T and I'll get to T hat. By the first three properties of the determinant, T is 0 if and only if the determinant of T hat is 0. Now, don't get me wrong, you could have swapped some rows, so T hat might be, the determinant of T hat might be negative, where the determinant of T is positive. That could happen. Or you might have multiplied a row by some number, and so the determinant of T hat is K times the determinant of T. That could happen, but the zeroness or non-zeroness will be unaffected. Now, of course, a non-singular matrix T, Gauss-Jordan reduces to the identity matrix. And so if we take the identity matrix to be T hat, then we get, it has a non-zero determinant. Again, the SIGN or the sign or the size could have changed in the course of the Gauss-Jordan reduction, but the zeroness or non-zeroness does not change. And then finally, if you look at we looked at the non-singular case. Non-singular gives non-zero determinant. If you have a singular T, then it reduces to a T hat that has a 0 row. And by the second sentence, then T hat's determinant is 0. And then since Gauss's method doesn't change the zeroness of the determinant, the determinant of T must have been 0 also. So one thing that you're seeing here, there's another part we have to do, but one thing that you're seeing here is that the argument is a little slicker than you may be used to seeing really even in this class, but also in sort of calculus or again whatever statistics class you might have had, whatever prior classes mathematics classes you might have had. So we are coming into something that we're starting with the very first sort of steps into some sort of more advanced mathematics, some sort of more abstract mathematics, which is exciting by itself for a person, but it also can be a little bit daunting. You say, well, this is not really the kind of way things I've succeeded at in the past have gone. That's right, but okay, so this just gives us something new to succeed at. I'll remind you what condition 4 is. Condition 4 says the determinant of an echelon form matrix is the product down the diagonal. So here we go. So the fourth sentence has two cases. If the echelon form matrix is singular, then of course the determinant of the matrix is 0. We saw that in the prior sentence, in the prior paragraph, which is the prior sentence of the lemma. And if you think of a echelon form matrix with a 0 row, multiplying down the diagonal at some point hits the 0 row, and of course at that point you're multiplying by 0, so the entire determinant is indeed the product down the diagonal. Okay. On the other hand, if the echelon form matrix is non-singular, then none of its diagonal entries is 0. So you're looking at something like this. Remember, the vertical bars here on the matrix means determinant. So you do the condition that allows you to bring out. So you multiply the entire you bring out, you bring out the T11 from the first row, you bring out the T22 from the second row, all the way out, so you bring out the TNN from the third row, and you'll remember that when you bring out T11 from the first row, it multiplies the entire determinant by T11. T22 multiplies the entire determinant by T22, and etc. Now you have ones down the diagonal. If you continue on with Gauss-Jordan elimination, you'll eliminate up. These things will go away, and you have all zeros there. You've got the identity matrix. The determinant of this is 1. That's condition 4. And you're just looking at the multiple of the TIIs. So the conditions enable you to get to echelon form. The conditions enable you to bring the TIIs out, although they rescale the determinant by a factor of TII. And then the conditions allow you to do the Gauss-Jordan part, and you get here the identity and without swapping any rows, so there's no sign change, and you're just looking at T11, etc. Okay, so here, the determinant of this echelon form matrix is indeed the product down the diagonal. There's no possibility of having to do row swaps, so you don't have to worry about sign changes. Okay. So all that, again, I'm aware of, I'm sympathetic to a person's sense that something is happening that they maybe never have seen before or not seen all that much. But we're now back on maybe more familiar ground, so that'll help a person feel like they haven't been steamrolled. So I'm going to take this matrix and perform the Gauss-Jordan familiar steps, Gauss's method steps, and get to echelon form. So this is a 3 by 3 matrix. I know we have a formula for the determinant of a 3 by 3 matrix, but I'm going to do Gauss's method on it. So minus 2 row 1 plus row 2, minus 3 row 1 plus row 3. I perform those 2 steps, and I got to echelon form. Now, those 2 steps do not change the determinant. So this says determinant of this equals determinant of this. That's condition 1. And determinant of this equals determinant of this. That's condition 1. Again, these combination steps don't change the determinant of the matrix. So I have the determinant is unchanged. And now I recognize this as echelon form, so the determinant is the product down the diagonal, whatever the heck that is, 14. So the determinant of this is 14, so the determinant of this must be 14, so the determinant of this must be 14. So Gauss's method allows us to calculate the determinant of a matrix. We're back to the definition of the function by its conditions. We're saying that we want a function that satisfies these 4 conditions, and the reason for those 4 conditions is not a big secret. The reason, the sort of higher level reason for the 4 conditions is they allow us to do Gauss's method to determine whether or not we get 0 for the determinant, to determine non-singularity. There's this business with the minus sign and the business with the k, again, is explained at greater length in the book, but from a higher level description here, these are recognizable as the Gauss's method steps. And so we find ourselves, not that what was here, was gibberish, but after some step into something that is perhaps a little bit not 100% perfectly familiar territory, we're back on calculating. And so we're going to calculate. One of the jobs of this class is to try to help a person get more comfortable with these more abstract ideas, because they are bigger ideas that you can think bigger thoughts with these abstractions, but we're always trying to make it concrete. So here we are back on concrete. The Gauss's method steps give us 14. 14 seems pretty concrete to me. Here's another example. Suppose I look at this matrix, and clearly in order to do Gauss's method, I got to start off by doing a row swap. All right, so do a row swap. That changes the sign. The condition tells me that one of the conditions in the definition of determinant tells me that I'm looking for a function that has the property that when you do a row swap, you change signs. Well, now I'm ready. This matrix is familiar. Minus row 1 plus row 3, and then minus row 2 plus row 3. I'm carrying the negative sign. See, this negative sign gets carried, and I end up over here. Ignoring the negative sign for the moment, this is an echelon form matrix multiplied down the diagonal. 1 times 3 times 1 makes 3. Along with the negative sign, I get a negative 3. So Gauss's method, keeping track of the row swaps, and also keeping track of any factors that you multiply, that you factor out of the determinant, Gauss's method enables me to calculate. the determinant of a matrix because the definition is exactly calibrated to allow me to do the Gauss's method steps, the most important of which are these combinations like minus rho 1 plus rho 3 and minus rho 2 plus rho 3. Okay, then, of course, I illustrated two of the conditions, so of course I'm going to illustrate the third. Here I have 5, 10, 3, 4, and here I have 1, 2, 3, 4. And the relation that condition 3 gives you is that if you factor out a 5 and you go to 1, 2, 3, 4, that doesn't just sort of multiply sort of half of the matrix so you get a 5 halves. No. Factoring out a 5 multiplies the entire matrix by 5. The determinant of the entire matrix by 5. So factoring a 5 out of one row scales the entire determinant by 5. All right, but the 1, 2, 3, 4 is not hard. We know the formula for the 2 by 2, so you can probably calculate it in your head right now. But I'm going to go through the Gauss's method step because that's what I'm illustrating. So I carry the 5, carry the 5, carry the 5. 1, 2, 3, 4 minus 3 rho 1 plus rho 2 gives you this. That's an echelon form matrix. 1 times minus 2 gives a minus 2. Don't forget the 5. The whole thing is minus 10. So the contrast is that when you multiply one row by 5, you get a determinant that is 5 times as big. So before we go on here, before we stop, I'm going to give you a caution. You probably noticed that AD minus BC has something to do with these diagonals. The AD and the BC has something to do with the diagonals. Some folks watching this will have learned in calculus class, I know I learned in calculus 3, that we didn't really learn what determinants are, but we learned a formula for the determinant of a 3 by 3 matrix, which is you write the first two columns down. Please, we're not going to use this formula. There's nothing wrong with it, but we're focused on something else. But I want to warn a person who may be misled. So I learned in calculus 3, you write down the first two columns. Then you multiply down those diagonals, the A, E, I, the B, F, G, the C, D, H, see them there? And then you subtract the backwards diagonals, the G, E, C, the H, F, A, and the I, D, B. And a person says, well, that's kind of like this. There's a forward diagonal, there's a backward diagonal. You subtract the backward diagonal. These two are kind of the same. Don't try, please, don't think that you've got it now. I understand the pattern. Don't try to extend it to 4 by 4 or larger sizes. Instead, the right thing to do, it's much faster, it's much easier, we're very familiar with it, so it's very hard to make a mistake. Use Gauss's method. So the purpose of the definition of determinant that I gave you, determinant is a function described by these 4 properties. The purpose of that definition is to use Gauss's method because Gauss's method is fast and accurate. So don't be misled into thinking, oh, this is what I learned in calculus 3 and I'm smarter than other people. I'm going to use, no, you're just fooling yourself. Okay, so I told that silly example of the function that does something with multiples of 5 and something with multiples of 2. So as we described before, the definition determinant, defining a function by giving conditions has a downside, and that is that we have to verify that there is such a function, and furthermore, we have to verify that there isn't more than one such function. So we have to verify existence and also uniqueness. Well, as to existence, somebody might say, how could there fail to be such a function? What do you mean? I've been computing the outputs. So I'm going to point out that you can do Gauss's method in more than one way. When I introduced Gauss's method, I, of course, introduced it by doing all the problems the same way because that's how you teach. You don't teach by saying, well, you could do this or you could do this. That's a good way to have a disaster. But it is nonetheless the case that you can do Gauss's method in a number of different ways if you choose to. I can take 1, 2, 3, 4 and do the obvious thing of minus 3 rho 1 plus rho 2. Or I could take 1, 2, 3, 4 and then swap the first two rows and then do minus 1/3 rho 1 plus rho 2. And you could say, well, why would you do that? But you could. Now, in this case, both of them yield the determinant of minus 2. Don't forget here that you swap the row, so if you're worried about determinant, you got to keep track that the determinant now will be the negative of the determinant of the starting matrix. But just because we got consistent results in this case doesn't mean that we have to get consistent results in every case. So the rule if you're thinking in your head something like, well, determinant is just, do Gauss's method, keep track of the minuses and the scale factors, and then at the end multiply down diagonal, you've got the right formula. That's how we're going to do it. You're absolutely right. But if you're thinking to yourself, why do I need to do more? The mathematical problem is that there's more than one way to do Gauss's method, and we have to verify that doing it by different ways won't give a different determinant answer. That's the problem. Okay. So we have to verify existence and uniqueness. Uniqueness will turn out to be easy. We're going to do it in such a second. But existence will turn out to be a bit tougher. Okay, so before I give any other ways to compute the determinant, that we're going to give a formula. Instead, I'm going to first do uniqueness. So in order to show that the determinant function exists, I'm going to give it an explicit formula for computing it, although it's a formula that you shouldn't use to compute it because it takes a long time. But nonetheless, I'll give a formula that'll solve the theoretical problem of is there such a function? But before we do that, I want to settle the problem of uniqueness. So I want to show uniqueness, that if there is a function satisfying the conditions that we gave at the start of this video, then there's in fact only one. So we'll find ourselves in, again, a circumstance that you may not have been in before, you likely not have been in before this class. So we are worried about whether there is a function, and we're going to show that the function exists. That there's a formula that exists, and so it computes the function, and it'll turn out to be a formula that we won't use, but we'll show that one exists. And then we also have to verify uniqueness. So we are going to, when I close the video at the end of this slide, we are going to know that the function is unique, but not know whether it exists. That's okay. I mean, you can only do so many things at a time. We're going to do uniqueness first. Turns out to be easier to do uniqueness. Okay, so for each n, if there is a determinant function, then there's only one. And the basic idea here is you suppose there are two, and you come to the conclusion that they calculate the same function. So you suppose there are two functions, det1 and det2, satisfying the properties, and you're given a square matrix. I'm going to show that they compute the same output for every square matrix M. So you're given a square matrix, you fix some way of performing Gauss's method. You might think that you're just going to write a computer program, and this computer program is going to perform Gauss's method to get to echelon form. Now my computer program and your computer program might not be the same program. Mine might, for example, for no sensible reason, start out by swapping the first two rows. So we might proceed by different ways, but nonetheless, we're just going to start here, fix some way. So in your mind, you fixed a way to perform Gauss's method that goes to echelon form. It doesn't matter which way, just fix one. By using this reduction, as in the above examples, keeping track of the row scaling factors and how the signs alternate, then we compute the value that these two functions have to return on M. My computer program always computes the same value for a given M. So det1 and det2, which says if you follow the rules, you'll compute a value, det1 and det2 have to work with my rules. So if det1 and det2 exist, they have to compute the same value for M, because the rules say, because they both accord with the rules. So if there is a function, I'm not saying there is a function, we will in the next video, but if there is a function, then there's only one function. Okay, so again, very mindful of the fact that a person is put, many folks in linear algebra are put in the position that they've never been in before, of thinking a little bit more abstractly about functions, and not that it's super hard, but just that it's a new circumstance, and a person can sometimes say, never been here before. Am I thinking the right thing when? Okay, so next time we'll talk about the properties of determinant, and we'll start developing the formula that computes the determinant function, and that therefore shows that there is a determinant function. Okay, very good.